Okay, so today we're going to begin looking at a very special kind of series which is going to open up a wide variety of possibilities for us, and that's power series. So power series is the key to huge amounts of stuff technologically about the way that machines work especially, but also higher level math. It's really the holy grail of this class, in my opinion. So a deep exploration of power series, and the next topic will be Taylor and Maclaurin series, I think is essential to being successful in engineering especially, and future math classes. And some even very good colleges don't spend enough time on this because you only take Calc 2 in a semester. So we're very fortunate that we get to spend a lot of time with Taylor series and power series. It's so important. For instance, all the things that your calculator does, all the things that any machine does with functions, it doesn't do them the way you're used to doing them, because when you think about things, you can imagine an infinite amount of stuff. Your calculator or any machine can't hold an infinite amount of stuff because its memory is of course limited. So it uses all kinds of tricks to get around that limitation of finite memory. And one of the main ways it perhaps does things just like draw functions like e to the x is it uses them with some power series representation. Okay, so power series are though going to build right where we left off with different convergence and divergence tests. So we're just going to take those and use them to investigate kind of a newish phenomena, but still a series. So most of it's going to be pretty similar. So I wanted you to, before we even talk about power series, recall something fundamental, is that functions can be expressed in a variety of formats. There's all kinds of different notations. So the most basic one you usually start working with in Algebra 1 or something like that is this f of x notation. And then you can have all kinds of things here based on what kind of function you have. Any combination of elementary functions, right? Or maybe even non-elementary functions you guys haven't seen yet. But mainly you're going to work with elementary functions, things like cosine, polynomials like x cubed, exponential functions, absolute value functions, maybe even something as exotic as a hyperbolic function that combines exponentials. I think we've seen that once or twice. But this is one notation. You'll sometimes in higher level math and other classes see instead of an equals sign here as like an arrow, because that's more like a machine thing, something being assigned to something else. The input doing this stuff to it with the gears of the machine and assigning it to something else. You can think about a function as just like an abstract machine. It's like some kind of Dr. Seussical machine. Who knows what's going on inside this machine? Give it a name tag like G, and then start throwing x's into it and get y's out of it. That's a much more abstract kind of function. What we're going to do today is see that power series can also be used to represent functions. That's the whole key. So I was thinking there was another calculus way to represent functions which we might be able to fill number 2 in with. I don't know if we know it well enough yet because we haven't reviewed for the AP exam. Can anybody help me? What's another way to represent functions using an integral? We had a special kind of function that we investigated right at the beginning of integrals. I called it an accumulating area function. And we started in some spot. We looked at some curve. That curve could be anything, so let's just label it as some random f of t dt. I'm just reminding you that you've seen other kinds of functions represented in different ways. And then you could start accumulating at 3 or wherever you want. You could accumulate from 3 to 6, you could accumulate from 3 to infinity, you could accumulate from 3 to some unspecified value x. And now this is an accumulation of the area under that blue curve, whatever it is, from 3 up to a variable. So this is a function in terms of which variable, x or t? X. In fact, if we were to write this out abstractly, we don't know the antiderivative since I just called it f, but we could write, what's the symbol we used for antiderivative if that's small f? Big F. And the fundamental theorem of calculus, part 1, says that this evaluates to big F of b minus big F of a, which in our case is 3. And that really is looking a lot more like old function notation that we're used to. But notice, something like this looks entirely different in terms of its eye appeal, but it's still representing a function of some variable input, this time the end of our accumulating area that we're investigating. Does that make sense to you guys? So it shouldn't be that surprising. The functions can be represented in lots of other different ways, and that's what we're going to be doing with power series. So for instance, e to the x we are going to memorize, because it's one of the most basic ones, can be represented by this power series. This is a power series down here. It's a series just like the other ones we've been studying. What's the only difference? There's an x in it. There's a variable in it. That's the idea that's different about power series, is that it's variable. Okay? So in order to approximate values of e, your calculator doesn't have a table in its storage bank for every possibility of what you could put in there. It does something like this. Now, it might not do exactly this. It might do something a little more sophisticated. But it does some variation of the power series of e to the x. So if you put in something like e to the 5th power in your calculator, it says, I'll just add up the first however many terms of this power series representation, chop it off, and call that e to the 5th power. Does that make sense to you guys? How does it decide where to chop it off? Well, it has margins of error, like we worked with beginning with our remainder theorems this year. And it makes a decision based on what margin of error the calculator deems appropriate, based on what you have in your mode. And that's where it chops off the power series, and it says, well, it's this, 2 point blah, 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 blah. But that's how it does computations. And if you guys are like, well, you'd have to chop it off where n is like really big, like 1,000, to get any kind of accuracy. How fast did some of our series that we've already seen this year converge? How many terms did you have to get a reasonable remainder, like within 0.0001? 7 terms. Is 7 a lot for a machine? A machine goes, please, 7 things? No problem. Even if it was 1,000 things, would a machine have a problem with that? Even your little puny little calculator? No, it'd be like 1,000, please. Got this. Might be hard for us, but a machine works differently. Things that are hard for us are easy for a machine. Things that are easy for us, sometimes hard for the machine. That's kind of what we're starting to study here. Okay? So that's my introduction to power series. Let's start doing some.
I saw it in chat.
Okay, so now I have the general version, or the definition, in other words, of a generic power series kind of on the board. And I wrote 2 different power series down, because there's really kind of two different ways to think about these. Well, not different ways to think, I should say. Just 2 we should be really comfortable with, okay? There's only a slight difference between the first general power series and the second one. First of all, I want you to look at both of those power series and tell me a big flaw that I have kind of theoretically in how they're written up there. There's something kind of missing, if you will. Look at them carefully, the first and second generic power series, and tell me what is wrong with what I have written down.
It goes to infinity, not goes to n.
How many terms should I be adding up?
Infinity.
Infinity. I shouldn't just be stopping at some arbitrary value of n. Doesn't this stop at some arbitrary value of n? What should I put to fix that? Now, in terms of actual mechanical calculations we'll do, that really doesn't make a whole lot of difference. But in terms of understanding how all this stuff works, that's really important, right? Because a series, if it's an infinite series, is infinite. And that, leaving it right there, is not infinite. It's finite for some value of n. So I should have that right here as well. Very good. Okay, so each one of these power series is centered in some specific spot. Think about the first one. What value of x is the center of that power series? That's a little bit of a hard question, whereas we're just starting out here, I know. Any ideas what the center might be if you just have x squared, x cubed, x to the n power? What are all of these revolving around? 0. This is the power series centered at 0. And And I think you're going to see why in just a second here, if that's still not clear to you. So if it's a little fuzzy, don't worry about it. I think it probably should be. So what's the only difference with my second generalized power series up here? It's been shifted where?
To the right C.
To the right by C. So that means it's the power series
Centered at C.
centered at C. Very good. So this guy is the power series, generalized one, centered at this generic C value. Now, of course, why does this matter? I'll start talking about it right now, which is the whole theme of this, one of the last 2 units we're going to do this year. And that is, when we use our calculator to approximate things, we of course need to have that series, whatever it is, whether it's a power series or a Taylor series, centered at where we're most interested in. So every time you tell your calculator to do something, it picks a center near where you're interested in and does it right there. So that's kind of a vague way to think about this as we start out. Okay, so what did I write down here? I think this last line is kind of redundant, but I just wanted to make sure that when you see this, what's one way to think about it besides an infinite series? You could think about it as a function of some input x, and that x right there is the input in the function. Okay? So I think that's one of the perspectives that you got to be clear on. I was not clear on this in Calc 2, but that's because we spent in Calc 2 like a week and a half doing this kind of thing. My friends who took BC Calc in high school spent a month and a half. You guys are going to spend a month at least, maybe a month and a half. That's the advantage of this class. We get to spend some time. So what I really wanted, besides that, writing that out one more time, is I wanted to emphasize the domain, because that's going to be big. The domain of this power series function f of x is the set of what? Can you guys help me maybe fill in this last blank? Domain is like where a function exists, right? So if we're thinking about a series function, what might need to be true so that we don't get something broken in our function? Think series. You have to be careful about what in series for them to be very useful. It not diverging. You need to try to make sure that the series converges. Otherwise, if this function diverges, it's not going to be very useful in approximating finite things, like we were saying for our machine, right? Does that make sense? So, the domain of this function is the set of all x values, because that's the input, of course, right? For which the function, I should say, the function, to make my grammar accurate, for which the function, which is a series, converges. So that's what we're really going to have to be concerned about, is making sure that when we're doing something with it, the x value that we're doing something with is in that, what we're going to call, interval of convergence. Okay? So we need to look at the possibilities for intervals of convergence when we do this guy. So I'm going to write this down as 3 rules. So let me start this guy out. Oh, I should have left that first one up there. I'll put it back. So I'm going to say, this is like a theorem. All power series do one of 3 things. There's no exceptions. So let's think about the simplest case first. So for like this guy up here, what did I say this one was centered at? I got to put it back up there. So if we imagine that specific center, what would we get? We'd get a sub 0 plus a sub 1 times 0 at its center, right? I'm not thinking about other places. Just at its center at 0, x equals 0, plus a sub 2 times 0 squared plus dot dot dot. And what would happen to all these terms? They'd all go away. So this part would all go away and we'd be left with just the first term. So is that convergent or divergent? Well, clearly convergent. Really simple, right? So that's one of the possible cases that can happen. No matter what the center is, if we were centered at some other c value and we plugged in c, you guys know what I mean? Like if I went a sub 0 plus, like in that second one from a second ago, a sub 1 times, and I plug in the center.
Pineapple or hedgehog?
So think about this. Did I pick one specific convenient c here, guys, or did I just pick the c that goes with the other c? I picked, yeah, totally. So what's going to happen here? 0. And here? And all the other terms in the power series out to wherever are all going to go away. So is that going to converge or diverge? It's going to converge. So no matter what the center is, the power series always converges at it, minimum. Does that make sense? So let's write that down. So all power series do one of three things. They either converge only at the center, whatever it is, I want to write this down really formally like I had it. So they can also converge everywhere pretty much. So we'll see examples of that. That's the best thing that can happen, but that's not as common. So even if they don't converge absolutely everywhere, it's not like all is lost. You just do other stuff instead. We'll see what that stuff is. So they converge only at the center. They converge absolutely for all x values belonging to the real numbers, in other words, everywhere. Or they converge. Sam?
Nowhere.
For some real numbers, but not for others. Let's be a little specific about that. But basically, you can think about it as they converge somewhere, if you like. So they converge within a certain radius, which we're very creatively going to call capital R. We're going to say that that radius is strictly positive. And so I'm going to put a little semicolon here and write it like this, so that they'll converge like this. This is the nice way to write that. Okay? What's this look like on a number line? Where's the center of our interval according to my notation? C, someplace C. And how far out in each direction do we go? Remember, you read this as the distance between your input values x and the center is less than r. So you go r this way and r that way to c plus r, c minus r, wherever those are. And all these x values trapped in there would be convergent. Now, tomorrow, or the next day, we'll see what time we're at. We're going to have to look at the edges as well. So you always have to check the edges of a power series as well. We won't do that today, though. We're just going to do a couple basic examples. Kind of ignore the edges for now. Okay, so let's look at some finite examples.
I'm still getting X and N confused.
Well, we need finite concrete examples. Hard without those, so that's fine. All right, so let's look at these couples power series and try to determine where they're convergent. Okay? So when you look at a power series to begin with, what should you focus on? What should you not focus on? Because one test that we learned about series is generally going to be the way to go, but not on every power series. You might want to go to another test once in a while. You don't want to focus on the x, because this series thing, does it have anything to do with x? No, its index is n. So x is, in other words, in regard to this thing, constant. This is changing. This is changing according to the series. So think about what kind of series test you might have used on this problem from before. Now, there's probably more than one option. What do you guys think? Ratio test, good choice. What else? I think I might have just picked
Like,
divergence test. The divergence test says that pretty much always, except when x is 0, because we're just going to get zeros added together. Except when x is 0, are we just going to be adding stuff up like forever? That's not going to converge, is it? I think the divergence test really says that this is going to be which one of those three cases? Only at the center is the right answer. But let's show it with the ratio test so we feel a little stronger, okay? So that's the intuition hopefully you already have a little bit of. Let's do it with the ratio test. So for the ratio test, can we do this? Yeah? Remember the divergence test, Sam, just for review, says that if you take the limit of the sequence, in other words, get rid of the sum, and it's not equal to 0, if it's anything else, then the series is going to diverge. That's what the divergence test said. So I'm going to look at this. Yeah, it's n plus 1, base of n plus 1. And then we're going to compare it to this guy. You guys tell me what to do next.
Multiply the x
Factorial.
So this is n
plus 1.
plus 1
Times n. Factorial.
times x to the 1. Yeah? Most of the stuff cancels in this problem, doesn't it? So we're left with this guy. Oh, I don't even need a bottom. The bottom's all gone. Okay, now the final result here is a little weird. How do we use the ratio test? Remind me.
If it's a greater than 1, it converges.
The distance between the next term less than 1 it converges. Otherwise, yeah, exactly. If it's equal to 1, you can't use it. It's inconclusive. Very good. Okay, now I've left out something kind of important notationally. Help me remember. The limit. Shouldn't there be a limit in front of all these steps? Yes, there should. Let's get it in there. I'll put it in blue. So limit, lim, lim. That's kind of important, I think, because like otherwise you'd look at that result and be like, is it less than 1, more than 1? I don't know. But now, so you should be able to look at this and think about what depends on n and what does not depend on n. Well, clearly, that does not depend on n, so what can you do with it? You can pull it outside the limit, right? Why is that helpful? Because now this you can evaluate. What's the answer? Infinity. What's infinity times any value of x, even if x were something crazy, like infinity itself? Infinity times infinity is not an indeterminate form, it's infinity.
Please pardon the interruption.
No matter what, then this is
Siemens 8-hour
infinity.
ag class will report to the shop. 8-hour ag will report to the shop.
Which is not less than 1, which means divergent, except if x was 0. Okay, you got to be careful on that. Note, nothing in the calculation really told you that. Except if x was 0 right here, what is 0 times infinity? That's an indeterminate form which you do have to manipulate. We're not going to manipulate it, we're just going to say, oh, thinking back to what we were doing this for, that means the center converges only. So we're going to say that. So we're going to say this power series converges only, key that you use that word only, at the center, x equals 0. Now let's do one more example before we leave today, so you guys can get a start on your assignment. So this power series, should we just do it the same way? Just go for the ratio test? I think that's what you want to do most of the time. Oh, and by the way, you can keep this 3 in, or you could put it right there and avoid it until the very end, right? So we're going to go x minus 2 n plus 1 over x minus 2 to the n, which is going to be,
Basically, x minus 2.
yes, ma'am. I'm going to show it though, just for anyone interested. Now, that guy, can you just pull this x out? No, it's got a separator that's like kind of combined with it, right? But you can pull the whole chunk out because none of it depends on n.
That's tricky.
So 1 is left. What's the limit as n approaches infinity of 1? And we were doing a ratio test, which means we're interested most in where this is less than 1. Do you think we can solve this little inequality and determine the conditional sometimes interval convergence? I hope so. So we've got 3. Now, you can do that inequality however you want. Remember from Algebra 2, the way I taught you, I think the best way to think about it is this. Centered at 2. You can float your 2 right there if you want. We're going to go inside or outside. If it's less than, you go out a certain amount. Less than is this. More than is farther away. So we're going to go how far in each direction, though? 1/3. 1/3 is our radius of convergence. So that's capital R, the radius of convergence. So we're going to go out 1/3 in each direction, so not very far, right? So right there to, 7/3 and 5/3. So that is our interval of convergence for that problem. Now, it might actually converge at the edges. It might happen at both, so I could put brackets. It might happen at just one. It might happen at neither one. We'd have to check each one of those values by plugging it back in for x and evaluating that series, which is no longer a power series, separately. We'll do that tomorrow, though, for an example. Okay? So the only case I didn't do was one that came out to be everywhere. I wonder what that might look like.
A line.
See if you can find a couple problems tonight. We'll do one tomorrow. Okay? See you next time.
Oh, pineapple hedgehog.